Hello. Welcome back to part 2. I hope you guys got some snacks, maybe got to move around a little bit. I'm going to introduce this topic of Aqueous Ionic Equilibria, which is chapter 17. I don't think I'm going to get too far into chapter 17 today, but at least I'm going to give an overview of where we're going with it. Okay. Aqueous Ionic Equilibria, what does that even mean? Well, what we're caring about here are aqueous suspensions of ionic type stuff and how these different types of things can have and behave in an equilibria setting. And one important topic of aqueous ionic equilibria are these solutions called buffers. These should be near and dear to all of you buffs out there, right? A puffer. Nope, not a puffer. A buffer is a solution that resists pH change. Okay, it resists changes in the pH. It will neutralize added acids and bases, and will neutralize added acids and bases. Okay. And a buffer contains either one, a large amount of weak acid and conjugate base, or a large amount of weak base and conjugate acid. Okay, so a buffer is essentially a large amount of either a weak acid and its conjugate base, or a large amount of a weak base and its conjugate acid. For example, there's a buffer in your blood that keeps your pH super constant within your body. Okay, this I will call the blood buffer. Sounds so creepy, right? The blood buffer. That'd be a funny Halloween costume. You show up to a party, everybody's like, "What the heck are you?" "I'm the blood buffer." I have no idea how you would actually dress up as this, but it would be hilarious, to say the least. The blood buffer, the buffer that's happening in your blood, is between carbonic acid and bicarbonate. Okay? Carbonic acid is acting as the acid, and bicarbonate is acting as the base, or the conjugate base. So the way, let's see here how. Okay, let's react some carbonic acid with base. If we add base into the solution, and we have a lot of H2CO3 in that solution, okay, we can neutralize this base and form just water, H2O plus HCO3 minus. Okay. Now, if we have if we add acid into the solution, we have a lot of bicarbonate already, and we can neutralize the acid with the bicarbonate to form carbonic acid. Okay, and these are both neutralized. Okay, so we have bad squiggles. Okay, these are both neutralized. That means that you can put either acid or base into the system and it still maintains the pH that it started with. Okay, so it maintains a nearly constant pH. And the way that it maintains that nearly constant pH, even if you're adding an acid or a base into the solution, is because we already have large quantities of both the acid and the conjugate base. So adding a little bit of acid or base into the solution won't change the pH at all because we have such a huge amount of carbonic acid and bicarbonate already. Okay, and to make a buffer, all you have to do is mix a weak acid with conjugate base or a weak base with a conjugate acid. Weak acids and their conjugate bases don't act as buffers in and of themselves. Okay, so even though you have some amount of carbonic acid and some amount of carbonate in the solution, even when you make a carbonic acid solution, right, there's still going to be a small percentage that becomes deprotonated, and they're going to be present together in the solution. However, this does not act as an acid, or this does not act as a buffered solution. A buffered solution needs two different sources of both the weak acid and the conjugate base, or the weak base and the conjugate acid. For example, if we want to make a buffer solution using the weak acid, acetic acid. Make a buffer using acetic acid. What we need is we need acetic acid solution. So we need a solution of CH3COOH, and we need a solution of acetate, CH3, oops. So we need a solution of CH3COO minus. We need that independent of the acetic acid. So the way we can get that, right, is we make up one solution of 0.1 molar CH3COOH, right? We just mix in some neat acetic acid into some water, and we can make a 0.1 molar solution. And we're going to add to that a solution of 0.1 molar sodium acetate. Remember, we can have these counter ions that are going to act as either an acid or a base. We can have these counter ions of ionic solution or of ionic compounds, and that's how we can get our independent form of acetate without having to deprotonate the acid. So when we mix these guys together, we will form a buffer. Okay, we have two independent sources of both the weak acid and the conjugate base. Now, what is the pH of this solution? What is the pH of the buffer solution? Because it has both the weak acid and the conjugate base in solution. So how can we figure this out? Well, we have a reaction, right? CH3COOH reacts with H2O to form CH3COO minus and H3O plus. Okay, this is our reaction. This is what we care about. We have initial concentrations, however, for the acetic acid and for the acetate. This we can approximate as 0 to start out with for the initial concentration. And because of this, we can, of course, use an ice table. Okay, we know that having some of this in solution will force the reaction that way, right? But we also know from Le Chatelier's principle that since we have some of this acetate in, this will force the reaction back to the left. So we have some sort of equilibrium, some sort of balance between the two that will be completely dependent on the magnitude of the Ka versus the Kb. Okay, so the pH of this solution, use an ice table. And we'll come up with a shortcut here in a little bit, maybe not today, but another day. A shortcut where you don't have to use the ice table, but you have to make some assumptions to do so. The nice thing about the ice table is that it always works. You can always use it and it always works. It's just a little time consuming. Okay, let's set up our ice table, ICE, And we have the concentration here, of acetic acid. And then on the product side, we have acetate and H3O plus, which is what we're interested in because we want to know what the pH of the solution is. So we start out with 0.100 molar, 0.100 molar. Let's say that we knew those to higher precision than what I wrote originally. The change will represent as the X is equal to the amount of H3O plus that we made. So we have to necessarily take away X from acetic acid, and we have to add X to acetate, and we have to add X to H3O plus. At equilibrium, we have 0.100 minus X plus 0.100 plus X and plus X for H3O plus. Okay, now we can come down here and we can set the Ka equal to the products, H3O plus times the acetate, CH3COO minus, over the reactant, CH3COOH, right? Ka for acetic acid, right? We're talking about this forward reaction of the acid reacting with water, so we use the Ka. And we can find that in table 16.5, and this is equal to 1.8 times 10 to the minus 5. All right, 1.8 times 10 to the minus 5 is equal to H3O plus, which is just X, times 0.100 plus X divided by 0.100 minus X. Now I'm going to assume that X is much less than 0.1. And this is probably true because if I just compare 0.1 with the Ka value, they're about 1,000 times off of each other, right? Or more than 1,000, 10,000 times off of each other. Which means that X will probably be much less than 0.1, so that's a pretty good assumption right now. We can come back and check it later. So now we have 1.8 times 10 to the minus 5 is equal to X times 0.100 over 0.100. These, of course, cancel out, and we end up with X is equal to 1.8 times 10 to the minus 5. If we check this now, up here, is X actually less than 0.1? We don't even have to run the numbers there. It's very much so smaller than 5%. It actually ends up being 0.018%, which is totally fine. So in this case, X is equal to 1.8 times 10 to the minus 5 molar. And that equals the H3O plus concentration, right? And we can find the pH finally by taking the negative log of that OH concentration, or H3O plus concentration. And this ends up equaling 4.74. Okay, so we have a pH of this buffer. And it turns out that this is the pH of the solution, okay, that you form between 0.1 molar acetic acid and 0.1 molar acetate. And this will stay at this pH even if you add some acid or base to the solution. Okay, so it resists changes to the pH. It will stay always at 4.74. But actually, that's not exactly true. If you add acids and bases, it changes the pH minutely. Okay, very, very, very tiny changes to the pH. And eventually, if you add enough acid or base, you can, of course, break the buffer. And when you break the buffer, then the buffer no longer acts as a buffer and it's completely consumed. And therefore, when you add more and more acid, it becomes very, very acidic. This is called the buffering capacity. And we'll get to the buffering capacity later on. I just wanted to introduce this concept of buffer for now and show you how a buffer can resist the change in pH. When we come back next week, I will go through some examples where we simplify this calculation, and not only that, but we'll actually calculate the change in pH that occurs when you add an acid or a base. And we'll see that the pH does in fact change, but it changes by a little bit. Okay, and that's the whole point of a buffer. It's to kind of slow down the change that happens because of an acid or a base being introduced. Okay, I hope you guys have an awesome weekend. I published chapter 16 homework, so be sure to take a look at that. Yeah, and we have this little meetup here in a little bit. Hope to see you guys there. Yeah, have a good weekend. McDonald out.